Well, hello, folks. We'll go ahead and get started. It's good to see you all. I know a few more folks will be joining us shortly, but let's go ahead and open up in prayer, and I'll give you a sense of what we're going to be talking about today. So, dear Heavenly Father, Lord, we just invite you here in our midst. Thank you for the chance to be working with each of the students in this course, Lord. I pray that the material will be clear, that the things that we do can actually be enjoyable, and they can see the linkage between what we're covering and the career and the positions and the kind of work that they will be doing in their future. Pray that you would help them in their spiritual formation, Lord, for all the classes that they're going to get a chance to take, exploring scripture, and the theological concepts in which we want to be familiar with, that these will be tools that they can use for the rest of their lives, and give them interesting and creative ways for faith integration. In Jesus' precious name we pray. Amen. Okay, well, today what I wanted to get a chance to have us discuss is we'll continue working through our textbook material. I'm going to be focusing on sorted lists. And so I'll go through the actual lecture there. And then there's a couple of video notes associated with that chapter. And then I'm going to do the relatively short video notes for some Java interludes that I think will be helpful. We'll talk a little bit more about generics. And then we'll also talk about the interlude on mutable and immutable objects. And depending how things are going, we actually have a third one. So there's just a lot of interludes here that I think might be of a benefit for us to get a better sense of some of the things that we have to be considering for the implementation that we're doing within Java. And then after that, I'll walk through something I posted on Canvas that gives us some greater insight into data structures. One of the things that I was having a difficult time trying to figure out the best way to explain quicksort. And so along with some other things, I think that might help there. And then we'll go ahead and go into Eclipse, and I'll start to walk through an example or two thinking about the sorted list. Okay, well, let's get into the sorted list. And so what I'm going to talk about here is give an overview. And so as typical, we introduce how it's used, and then we get into thinking of how we're going to do the backend programming to create. And here we're talking about a sorted list. And then we'll be thinking about the implementations. We'll talk about a linked implementation. And so we'll have an array implementation and a linked implementation when we look at the video notes. And I'll actually talk about two different ways you can actually create a sorted list. You can actually use list and then just make re-implementations of the three new methods that have to be changed to have everything be sorted, and you can see what that looks like. And then we'll finish up by talking about the efficiency issues that are associated with each of these. And I think that will be informative for you to see how that works and why it is actually better to use a sorted list rather than modifying a list. Okay, so we've already talked about lists, and so list is entries in a list are ordered simply by position within its list. And so you just add an item, and it's defaulted. We saw with our backend implementation, it typically adds to the end of the array or the beginning of the linked implementation. So you can add a sort operation to the ADT list. So that is definitely a possibility. And there may be some situations where that's maybe the best or the only way that you could do it. So you can add an entry, remove an entry from the sorted list. It provides only the entry, no specification where the entry belongs or exists. And so that's the specifics there. So now we want to be thinking about a sorted list. And so we know that the data is a collection of objects that are put in a sorted order. So every time you add, remove, or you seek to get a position, we wanted to, you have this information that it's in a sorted order. So that's actually going to be quite helpful. And so it's also, as we've seen before, it's nice to know what the number of objects are in the collection, and that's a variable we'll keep. And so we're going to be focusing on these new ways of doing these three methods when we're doing this now. Every time you add or subtract, it's going to put it in the proper place. We saw some examples. Well, if you manipulate it in the application side, you can do some of that, but it puts a lot of the onus of this that isn't necessarily something that you would want a user to have to deal with. So these are all the same. These are the other methods that are in the ADT list: get entry, contains, remove, clear, get length is empty, and to array. So those are going to be exactly the same, but those other three are going to change. So here is the sorted list interface. And so instead of a list interface, we put sorted. So we use a nice naming convention to help us to get a better sense of what we're talking about here. And so, so the first one for add adds a new entry to the sorted list in its proper order. And so the size is increased by 1. So that was the first one. And then for the remove, it removes the first or only occurrence of a specified entry from the sorted list. That's going to be something we're going to come back to when I show you this thing that I posted on Canvas. It's actually a C++ way of looking at data structures. But here, in a sorted list, in terms of a data structure, you can have more than one of an occurrence of something. And then finally, remove. This is something that gets a position of an entry in the sorted list. I'm sorry, the get position. It gets a position of an entry in the sorted list. And it's actually going to be easier since it's in a sorted order. You're not going to have to look as far to find what the result is. So we have these already from the list. And so we just kind of did a shorthand so we could combine them all quickly on one slide. And so we have that information. So let's think of a linked implementation of a sorted list. And so just to have a quick question. So what is the private class that we need to have when we do a linked implementation? Anybody remember what that private class would be? What's the name that we have used? Anybody remember that? Well, actually, we have it here on this slide here. It's the private class node, and so there's more complexity that we want to be doing with a node, and so having a private class is a great way to do that. And so here we see for this implementation, we implement the sorted list interface. We just talked about that. We do have this funky kind of construct, and so just go ahead and copy that verbatim. So you have these angle brackets 2 times the angle bracket for the linked sorted list, and then we have inside that angle brackets we have the generic type T, and it extends the comparable for all these things. When we're trying to do sorting, we need to be able to compare something, and then we have this other construct here that you over time, I think this will start to become a little bit clearer exactly what that's trying to help us to get a better sense of. And so that implements the sorted list interface. We create a first node, and it is of a type node, which we define lower in this class. And we keep the number of entries. We found that it was especially helpful when we do a linked implementation to help reduce the complexity, so the big O notation is actually less. Then we get into the default constructor for a linked sorted list with no parameters. And so we put, we don't have any links, and so that's null, and the number of entries is 0. And so that ends that. Then we have the implementation of the sorted list operations. And then we have a private class and some other private methods stuff that we have that we'll get a chance to be thinking about. So this is a characteristic of what it would look like in a linked sorted list. So you have Allie, Bob, Jill, Mike, Sue. These are all the things here. So first node is Allie. And so Allie is less than Bob. Bob is less than Kathy. Kathy is less than Jill. All of these types of things that we're seeing, we can do these kind of queries. So right now, what we have here is Bob, Jill, Mike, and Sue. So if we wanted to figure out where to put Allie, we put it here. Want to figure out where we're going to put Kathy, it's going to be in here. Luke is less than Mike, so we put it here. Sue is exactly equal to Sue, so we would be putting in an extra Sue, if that's what we're being called to do. And finally, Tom is greater than Sue, and so we would have to put another element here, another link at the end of the chain if we were going to add Tom. So that just gives you an idea of what it would look like. So with adding, we know everything up to that point has been put into the proper order. So this is giving us a nice heads up for where we're going to actually be adding it. So this is the pseudocode. I'm not going to walk through it in detail, but you can get a general sense based on what we were doing, a real quick thinking about it here with this previous slide. Then we have an iterative implementation of add. So we set up, we have a couple of things here. We have a new node that we're going to be adding. So we're going to be adding a new node. And then we have another one that we have the node before. And so we have a private method we'll see in a minute, the get node before of a new entry. And the new entry is what we pass to this method. So then we have an if-else statement here. If it is empty or the node before is null, then this gives us a construct that we want to be adding at the beginning. So this is how that would work. Else, we're adding it any other place than at the beginning. And so these are the things that we do for that. And then finally, we increment the number of entries. So the thing is, the trick is we want to put it in the right place, and we have the knowledge that everything is already in its proper order. So that's going to make it easier for us to accomplish that, as I already pointed out. And so this is how we can see that some of this code can be a little bit streamlined. So this is the general method add in an iterative sense. And then we have the private method get node before. And so this is where we see that the coding strategy of the authors, that they like to package things. And so then we have a private method get node before. We could call this in multiple different places if we so choose. So we have the current node, and then we have the node before. We set it to null, and then we have a while statement while the current node is not null, and the an entry is that we do is greater than 0. Then we actually do this process. The node before is equal to the current node, and the current node is equal to the current node dot get next node. And we do this until this is not no longer satisfied, and then we actually are able to return the node before with a proper value. So we can also be thinking of a recursive way of how we would be doing this. And so we'll get a chance to be seeing this in the video notes. And so I'm not going to dwell on this as in much detail, but this is just some of the material that we have in the lecture notes to help us get a better understanding of what's going on. So here we see the recursive implementation. So recursive means that we have the 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 method itself is called inside the method. And so here we have a public and a private. So this first one is add, and then what it does is it calls the private version of that, and this is where we're going to be seeing that recursion show up. So here we see the add here, and then we have the base case that's up here. So we have this thing here. So the current node is exactly equal to null, or the new entry is less than or equal to 0. Then we have this case here. So we're going to be, we have that scenario, and then we have everything else for this other scenario that we do. And so this is a recursive implementation. And so we have the add here, and so we have like the one less than what we had before. And so that just gives us an example. So we don't have to traverse the whole length of the chain. We traverse one less than we had before. And I think this is what we're trying to show here with these cartoons that we have, trying to show the linked implementation. This is just some more details, and I'm going to let the video notes give a better sense of giving us a chance to see what this is all about. So this is going to be the first. We're going to actually see comparisons of implementation. This is the worst case efficiencies of the operations of the ADT sorted list for two implementations. One is with an array and one is with a linked implementation. So you can kind of scan here. We can see the get entry. It's easier for doing this for an array. And so maybe we might want to think about doing things in an array implementation versus a linked implementation. So we're going to come back to this. This is actually using this sorted list, but we're also going to be thinking about, well, what if we use a list and then just added these extra methods? How well does that perform? And we'll see that at the end of this this chapter lecture that I'll be going over. Now we'd be thinking about it. What would all this look like if we did the ADT list versus the ADT sorted list? That is definitely a possibility. And so we see that we have a couple variety of methods that are in the way of using a list, but then we have a few other things that have to be done in a slightly different manner. So here we have a sorted list that extends okay, so here we have a class that implements the ADT sorted list by using an instance of LList. And so we actually are going to be using the sorted list interface, but when we get into some of the details, here's what we see an example. Instead of using a sorted list, we're using a list. And so that means that we're going to have to be doing some special things with some of the methods to make it a sorted list. And so here we have some, we have to use a math application to help us figure out where exactly we're going to be putting into this. What is the new position? And so this is one of the changes that we're going to be using for that. And so for the, this is, let me see, this is trying to remember if this is a linked implementation or array implementation. Anyway, it doesn't spell that out real clearly so far. So we have the add, we saw that. Then we have, this is how we're going to be doing the remove. And so this is the basic implementation of what that would look like here, okay? So this is gives us a picture of what we would want to do. Say we want to put Jamie in the middle there, that would give us an example of that. And this is the implementation that uses the ADT list as compared to what we did doing it from scratch. And so there's a few other things that need to be done. And we're getting a chance to see a little bit here. This is the other one that needs to be modified, the get position. And so that's that. So here is just two charts that I'll just finish up here. So this is what we see with the implementation of the sorted list, what we introduced for this chapter. So we saw that there was one example where an array implementation works a little bit better. But now let's compare what things would be if we did it with using the ADT list and just modified a couple methods. Well, we see that the linked implementation, there's several cases where it's n squared, so that's definitely not something that we would want to do. And so maybe if we did things with an array list, it might be something that would be okay, but definitely we wouldn't want to be doing an implementation using the list versus the sorted list because of this huge kit that we're going to have there. Okay, well, those are just a few points I wanted to go through before we go into the video notes. Let me see, any comments or questions on that? Or you can just give me a thumbs up if you're tracking with what we covered there. Okay, good. Well, I'll continue to help out and go over some other material that I think will also provide some additional information. So let me just point out where I put this link. And so I'm sure there's various other things that you could find. So if you go to the bottom of the section for the course resources, there's something called C++ Data Structures and Algorithms Cheat Sheet. And so this is what I'm showing here. And so I know we've been using Java, and so some of the nomenclature is a little bit different, but it's useful for us to be thinking about this in the future. You might end up having to do some programming in C++. So we've talked about some of these. We talked about DEC, we talked about list, we talked about stack and queue, priority queue. We haven't talked about heaps yet, but that's going to be coming soon. They have a couple other terms. Like for map, this is something in Java, it's called a dictionary. And so we'll get a chance to be seeing what that's all about. Vector is an array that automatically resizes. Java also has that. Set, we're talking about a list. And so say like if you had like and you put in two ands, you would have a unique one for each one of those. A set is different, that if you keep adding and it's only going to have one and in that data structure. So that's a different type of a data structure that could actually be a useful thing. You can see there's some nuances that we're starting to get exposed to of what actually can be done in certain terms of data structures. We haven't talked about trees, but we have began to introduce this idea like a depth first search or a breadth first search. I've also been talking about binary trees, at least I've mentioned that term. And so I'm just going to show some of these things. And I may come back to this again in the future. And they also have some visuals for some of these different types of algorithms for sorting, including the quick sort. And so that's one of the things I want to make sure that we can get a chance to see what this would look like. Okay, so they list a variety of different data structures. Even we had like a linked list, and so a singly linked list and a doubly linked list. And so we got a chance to be seeing that with a DEC, that you can have access it going in both directions. Now we started to see a variant here, which could create another type of a data structure that might actually be useful. So that's something that we have here, a binary search tree. We're going to be coming to that. They talk about a bunch of other trees that we haven't had a chance to talk about yet, nor have we talked about a hash table. This is something that we'll be getting into soon when we start to talk about dictionary implementations. They have an interesting flow chart that helps you to determine, well, what do you want to be doing with this data structure? And it helps guide you to what they would recommend for that data structure. Then they have a little section for each of these data structures. I'm just going to skip over this for now, and I'm just going to go down to the visuals because I already gave a little bit of an introduction to these at the very beginning. Then they have the visuals here. So this is the first one. It talks about a binary search, and you can be thinking about this in comparison to a different way. And so what it does is it starts out at the very beginning. A binary search, you have to go, a linear search is you just go from one to the end. And let's say that the right answer is right in the middle, and we can be starting to see how each one of these compare to one another. Binary search is either the upper half or the lower half, then it divides into a quarter, divide this into an eighth. So that gives a comparison there. But what if the correct answer was way over here? You can see that this linear scan is going to take a long time. But if there's a binary search, this is a if it is a sorted list, it's actually going to converge on that a lot faster. This is what a depth first search looks like. And so you might have picked this up as we were looking through some of the stuff that we've been seeing from our video notes. But basically, you go one down, all the way down one line before you go to the next one. And there's an algorithm for doing that. Then we have the breadth first. And so here we can see how we just get the order that gets things laid out there. And then I'm going to skip down and talk about first about the insertion sort. And this probably will look familiar to you to see how it goes. That basically this started in the middle when I picked it up. So sorry, you're seeing it about all the way, most of the way done, but it'll recycle in a second. So in the insertion sort, it has to move everything out of the way and put things where it goes. Since we've already covered this, this probably will make sense what you're seeing here that's taking place. So this is something that's relatively speaking, it's easy to be tracking what is going on. A selection sort, it gives a different way of visualizing it. So this graphic down here, I think is helpful for you to be seeing how it's going. And so basically, as you've gotten the more and more of it sorted, then you don't have to keep going back and through that all. It's just the ones that are remaining. So here we see that growing number of things that are sorted, and so it gets faster and faster as you get down from there. Well, there's a couple others that we haven't covered in class. We haven't talked about the bubble sort, so you can spend some time looking over that. I'm not going to focus on that. We talked about a merge sort, and I think this was something that was relatively straightforward for you to see, to capture, to see the flow of it. It's like a divide and conquer. And so this we can see one step at a time. And so the graphic on the top is showing a larger number. So you aggregate it into parts, and then you merge those parts together. So for this example down here, we break it up into two, and then we put those in the right order. then we merge the two of the twos into one, and the other two of twos into the other, and then we finally do the merging of 4 and 4. So that's what we see with that. And finally, we have the quick sort, and this is the one that's a little bit more difficult to maybe come up with an intuitive way to be thinking about it, but they always talked about putting something at the end. So you start with a whole, then you divide it in half, then you divide it into quarter, then in eighths and sixteenths. And so this graphic kind of gives you a chance to get some idea of what that would look like. And so this doesn't perform quite as well as a merge sort, but it still is something that's available to give you a perspective. Okay, let me just double check. You guys tracking what I shared there? Does that make sense? Does that help? That's probably a better question. Okay, well, let's go on and look at the video notes now. And so the first thing I'll do is I'll do two Java interludes, and then I'll do the 2 video notes on sorted list, and we'll focus on that. So let's go ahead and do the first of the Java interludes here.
Many of the classes we've studied so far have private data fields, and then we added public methods that either look at or change these fields. As we know, such methods are called accessor methods and mutator methods, or alternatively, set and get methods. An object that belongs to a class as public mutator methods is said to be mutable, because the client can then use the set methods to.
So mutable means that you can mutate it, you can change it. Maybe just a way of having you think of that word. Unmutable means that you can't change it. And so thus we're getting a chance to think a little bit about, in terms of cybersecurity, what are you giving access to the user and what can they do with it? And so do we actually want to give them the gold standard, or do we want to give them a copy of that? So if they manipulate it, we're not going to have our gold standard damaged.
To change the values of the object's data fields or mutate it. For example, we saw the class name of 2-part names in an earlier lecture. It has the 2 data fields, first and last. To change these data fields, the class has mutator methods set name, set first, and set last. To look at the fields, it has accessor methods get name, get first, and get last. Let's use this class to create an object for Joe Gomez. Now suppose we create a list and then add Joe to the list. Since Joe is a mutable object, we can change its data fields by using the setLast method. After this change, the object Joe represents the name Joe Smith. Nothing is surprising here. What might be surprising, however, is that the list has changed also. That's right. If we retrieve the first item in the list and print it, we'll get Joe Smith instead of Joe Gomez. How can that be in the list, which we created before changing the name, and now the list contains the changed name? Remember that in Java, the list contains references to the actual objects that the client places in it. So the list has a reference to its first item, but so does the client, since it has the variable Joe. When we altered the object, we changed the one and only copy of that object. Since the list still references that object, name get entry 1 will return a reference to the object. This aspect of Java can be a convenient way for the client to alter the objects it's placed in the list. The ability to mutate objects in a collection can permit a client to destroy the collection's integrity also. For example, suppose that we create a sorted list of names instead of a list of names. If we added 2 names, Jesse Java and Rob Bean, we would get the sorted list shown here. Now, if we set Rob's last name to Smith The list looks like this, and the sorted list is no longer alphabetical. One solution to this problem is to require the client to use immutable objects in our sorted list. An immutable object is one whose data fields could not be altered by a client. The class to which an immutable object belongs has no public mutator or set methods. So once you create the object, you cannot change its data fields.
So it's
If you
read.
need to change the item,
So it's from a user's perspective, it's read only. They can't write to it, they can't change it.
you'll have to discard the object and create a new one with the revised fields. Such a class is said to be read-only. A client that places immutable objects into a sorted list could not alter those objects and thus cannot destroy the sorted order of the list. Most classes have set methods, so their instances are mutable. But being able to change an object's data is convenient and efficient, particularly when an object's state must change often during the course of a program's execution. For example, a bank must regularly update the object that represents your checking account. If that object were immutable, it would be discarded and a new object representing the updated data would be created each time there was a change. But revising an object takes less time than replacing it. On the other hand, sharing a mutable object can be dangerous. Suppose that you have two references, A and B, to the same object. If you use A to modify the object, you might get confused when you use B to reference it. But sharing immutable objects is safe, since no matter how you reference them, they remain unchanged. Let's convert the previous class name into a read-only class and call the resulting class immutable name. Suppose the immutable name had protected mutator methods such as set first and set last. A programmer could use inheritance to alter the behavior of this class. Imagine deriving a class of mutable objects from immutable name. You could then add instances of this new class to a sorted list of immutable name objects. And since these entries are mutable, you could change them and destroy the order of the sorted list again.
So you can see from a cybersecurity point of view, this is a good thing to do. You're also trying to maintain the integrity of your master copy. It's also good. There's reasons for just good coding practice. There's a variety of reasons of why this is a good thing to be considering.
To prevent this from happening, we can make the class final. We can change the access modifiers of the methods set first, set last, and set name from public to private to prevent a client from invoking them. We could instead omit these methods altogether, modifying the other methods that invoke them. We also omit names method give last name to. If we place instances of immutable name in a sorted list, we'll not be able to change these objects by using any references that we might have retained to them. Of course, we can use the replace operation of the ADT list to replace a particular item in the list, but no such operation exists for a sorted list. To change an entry in a sorted list, we would remove the entry and add a new one. In this way, this sorted list could maintain its sorted order.
Okay, so some of these video notes are useful to just give us a perspective of how to best protect data. We're trying to use some functionality maybe in ways that you haven't been exposed to. And so those are just some things that are there. Now, let me check have you guys heard of inheritance and polymorphisms, or those terms that you guys have heard? If so, just do a thumbs up if you okay with that. Okay, so there is some familiarity with these ideas. And if you haven't, don't worry about it. I'll try and make sure that I give you a sense of what that actually is all about. But I think this video note will show you how we're going to be leveraging that, but also introduce the ideas.
In this lecture, we'll discuss inheritance and polymorphism. First, let's review Java interfaces. Java interfaces provide a common signature for methods. Here we can see the Shape2D interface that we used whenever we implemented our square class and our circle class in the previous lecture. We can also implement an oval class, a triangle class, and a rectangle class. Similarly, where the implementation-specific private data fields and constructors would vary, but each of these classes would implement the methods in the Shape2D interface. So let's look at polymorphism.
So in case some of you might be more familiar with how you look at words, but poly means many and morphs, many forms. And so this is what we're going to see, that we can have like a method, but depending on what you pass in that method, it can actually make it go to one instance or another.
To explain polymorphism, let's look at an example first. We want to create a simple shape test program. It'll create a square followed by a circle. It'll compute the area of each shape and then draw the shape. After that, it'll write the area for the display. So the output of our program would look something like this. Let's implement our drawing code in a class that extends JPanel called ShapePanel. First, we'll instantiate an instance of a square and a circle. We'll then compute the area of each. Then we'll draw the shapes. We'll create a decimal formatter in order to format the output to 2 decimal places. And then we'll draw the string area is followed by the area of the object. As we look at this, there's a lot of duplication. We have 2 statements here that are very similar, calling the draw shape method of the square and the circle. And then whenever we do the writing on the screen, again, 2 method calls that are very similar.
So, for this example, using polymorphism, you'll see in just a minute, it's going to simplify the code. And so we're not going to have all these multiplications of doing very similar things one after another. I would argue, say for the first time, if you were going to do this program, you might want to do it this way, and then you could streamline it, getting it more maybe easier to follow in one way, but harder in another, because now you're having to have a better understanding of what's going on with Java. But let's see how this unfolds.
Whenever we have a lot of statements that perform similar actions, it's a good time to consider creating a new method. Let's create a private method called display shape that could take care of this for us. Now, each of those methods we used earlier were part of the Shape2D interface. We're going to send a Shape2D interface object to our method. Now, inside our method, because we declare this as a Shape2D interface, we can only implement methods that are in the Shape2D interface.
So by now, this should be familiar to you. This is a UML way of showing this information. And so this is an interface. And so with the plus signs, all of these are public. These are the things that are passed. And the things that are passed to the method and the things that are returned, what kind of characteristics it is.
If the class we send it implements the Shape2D interface but adds additional methods, those additional methods will not be available to us. Here we can find the area, display the shape, and then write the area on the display. Now to get the location, because the only methods available to us are the methods defined in the Shape2D interface, in order to determine the location to draw the string, we need to call the getLocation method on the shape, and then get the X coordinate and the Y coordinate to pass to the drawString method. We can go back to our paint component method now. We can create a Shape2D interface object called mySquare and assign a square to it. We can do this because a square implements the Shape2D interface. Notice that in our diagram, square and circle are below the Shape2D interface, indicating that they implement that interface.
So we're going to see 2 examples, a square and a circle. They're going to be using this Shape2D interface. And so if we end up having the square instance versus the circle, it's going to do something slightly different.
A circle we can create the same way we did earlier, and yet we can still send both of these to our method because the method is expecting an object that implements the Shape2D interface. We can also define circle as a Shape2D interface object, and the application will perform in the same way. Well, what is polymorphism? Here in our display shape method, you see we call the get area method, the draw shape method, and the get location method. All of these methods are defined in the Shape2D interface, but not implemented. The version of these methods that's called cannot be determined by the type of the variable, the shape. The shape is a 2D interface object, and it doesn't have any implementation. Our program has to wait until the display shape method is called and actually executed to see what kind of shape is sent to it. Then it knows what action to perform for each of these methods. In our example, the first time the display shape method was called, we sent it a square, so the get area method of the square class was called, the draw shape method of the square class, and the get location of the square class. The second time we called our display shape method, it was sent a circle. So the circle version of each of these methods is called. Because the version of these methods that will be implemented cannot be decided until the program runs, this is called dynamic binding. In our example here, the variable, the shape, is said to be polymorphic because it's able to reference objects of different types. All those types must implement the Shape2D interface, but the specific implementation we won't know until the program runs. Therefore, the shape is a polymorphic variable. And when we call the method of a polymorphic variable, such as get area, draw shape, or get location, the determination of the implementation that will get executed cannot be made until the program runs.
So far, in terms of shapes, we've been introduced to, well, the final, what's going to happen is either going to be a square or a circle.
The Java interface defines methods that other classes will be implementing. And the actual details of the implementation can vary greatly between the different implementing classes. What if we want to have a common behavior among a group of classes, and our design maybe results in common data fields for a group of classes? For example, we might have our circle class from our previous example, but also we want to have another class called colored circle that allows us to draw circles with various colors. We can use inheritance to help us out here. Since we've already implemented circle, we don't need to re-implement a lot of the details.
So we can have circle and it defaults to black, and then you have colored circle, it extends circle, and now we can have not only that we have a circle, but we can actually select the color.
In order to implement our colored circle class, we can inherit those details. So for our colored circle class, many of the methods are going to behave similarly. The area of a circle will be determined the same way. The perimeter, being able to set and get the location, can be done the same way as in the circle class. We do need to change the draw shape method to set a color for the circle. Therefore, we'll need to add a color field to our colored circle class and initialize it in our constructor. And then we're going to add a get color method in order to report the color. So we'll be able to reuse some of what we did in the circle class here in our colored circle class, but there are a few variations. Our colored circle class needs to extend what we did in the circle class. If we look at a UML diagram, you'll see that the colored circle class falls below circle class because.
So the more specific for a UML diagram here, it's down at the bottom. You do the implementations of the interfaces, either a square or a circle, and then we get more specific with a colored circle.
It's going to extend what the circle class does. The circle class in this instance is considered a base class, and the colored circle class is a derived class. So when a class extends an implementation, it's considered a derived class. The class that is extended is the base class. The derived class is going to inherit properties and behaviors of the base class. Another way to refer to the base class is as a superclass, And another way to refer to the derived class is as a subclass. So let's look at our colored circle implementation. We're going to import graphics and point as we did earlier for the circle class, but now we also need to import color because we're going to be working with color objects. Our class, colored circle, is going to extend the work already done in the circle class. We need to add our data field, the fill color data field, and then we can implement our constructor. Our constructor needs to accept a color parameter so that we can set the color of our object. In order to initialize the circle's radius and its location, we need to call the constructor of the circle class. And we do that by saying super, and then send it the parameters that it's expecting. We cannot directly set the radius and the location from within our subclass because those fields are declared private. We'll talk later on about how we can get around that in a future lecture. We'll discuss how we can design our classes so that subclasses will be able to access our data field. But for now, we'll just use super to call the constructor to initialize the private data fields.
So you can do that with a package access, which you've probably heard me use that term, but we'll see that.
In the super class for us. We can then initialize our data fields, and then we implement our extra method called getColor that'll return the color that we are going to draw the circle. And then we are going to implement our new version of drawShape. Our new version of drawShape will get the old pen color so we can reset it later, set the pen color to the color for this circle. We'll then call the drawShape method in our super class or base class. We need to do this because we don't have access to the point class. And also the code's already been implemented. We don't need to re-implement it again. After calling the drawShape method, we can then reset the pen color back to the old color that it was before our method ran. When we rewrite a method of the base class, this is called overriding. When we override a method of our base class, we need to make sure that the signature of our method and return type match what's in the base class. A derived class is going to inherit the properties and behaviors of the base class, but it will not have access to anything declared private in the base class.
Okay, so useful just to get some perspective of what's going on behind the scenes that we need to leverage in Java. But now let's look at these two different approaches here. Well, first we'll talk about the linked implementation, and then we'll talk about arrayed implementation of a sorted list.
This lecture describes the operations of the ADT sorted list. If your application creates a list and then at some point needs to sort the list entries into numerical or alphabetical order, you can add a sort operation to the ADT list. You can use one of the algorithms given in earlier lectures to implement this operation. But when your application requires only sorted data, having an ADT that orders the data for you would be much more convenient than the ADT list. The sorted list is such an ADT. When you either add an entry or remove an entry from a sorted list, you provide only the entry. You don't specify where in the list the entry belongs. The ADT determines this for you. Let's see what the specification for this specialized list would look like. One difference from the ADT list is that our sorted list must have comparable objects if we are to place them in an order. The add method takes an entry to add to the list. The client doesn't specify a position.
So we've seen this funky type of construct here, but now you're probably getting more familiar with it. That it needs to be comparable. And so that's all being laid out here.
The ADT will determine the correct sorted position for this item. Since the client could not make an error in determining the position as in the ADT list, the method does not need to return a Boolean to indicate success or failure. There are two remove methods in our ADT sorted list. The first searches for a client specified entry and removes the first occurrence of that entry. We'll see in future lectures, because our list is sorted, we can implement efficient search methods. This method returns a Boolean to indicate that either the entry was found and removed, or it was not found in the sorted list. The second remove method is similar to the remove method in our ADT list, and the client must specify the position in the list of the entry to remove. Since the client does not control where in the list items are stored, many ADT sorted list specifications do not include this method. To find where in the list an entry occurs, we need the get position method. This method searches the list for the client specified entry. If the entry is found, the position in the list is returned. If the entry is not found, a negative number is returned to the client. This allows the client to differentiate the success or failure of the method, since the position of an entry cannot be negative if it exists in the list. The other methods in our ADT sorted list specification are similar to those in the ADT list.
So we saw this in our lecture notes that I went over quickly. The only variant is that there are two possible removes. We didn't talk about the second one that they said sometimes is not even included because we don't know exactly where the position it is in the backend implementation.
Our sorted list only needs a reference to the first node of the list, since we'll not be adding to the end of the linked chain unless we've verified it's the correct sorted position for the entry by traversing the chain. Our constructor initializes head to null and number of entries to 0, since we're beginning with an empty list. The challenge for the add method in our sorted list is finding the correct sorted position in the chain to insert the entry. We can see how the method behaves by using the example of inserting oranges into our sorted list. First, a new node is created for us to insert into the chain with the entry as its data. To add a node to our sorted list, we must have a reference to the node that comes before this node in its sorted position and the node after it in its sorted position. In our ADT list implementation, we had a method getNodeAt that returned a reference to the node at a specified position in the list. When we added and removed nodes from our list, we called this method by sending the given position -1 in order to find the node before the node we wanted to add or remove. In our sorted list, we don't know the position of the node to add or remove until we encounter it as we traverse the sorted list. But to add or remove a node, we still need a reference to the node prior to it in the list. We'll use a private method, getNodeBefore, that searches the list for an entry, but stops at the node prior to that entry and returns a reference to that entry.
So once again, we have a private method. We're not showing it here, but it's going to call a private method for doing this code.
Let's see how we could implement this. We begin by creating a reference current node. This will reference each node as we iterate through the chain. We can use these to find the entry we are looking to remove, or in the case of our add, the first entry that is greater in value than the entry we're trying to add. We then create a reference to the node prior to the current node in the chain. At this point, the node before is null, since there's no node before the head of the chain. Our add method can test for this value when determining if the add will occur before the first node. This could happen if the value of the entry we're adding was less than the value of the current first entry in the list. For example, acorns here. Next is the while loop that iterates through the chain, searching for the entry or where to add the entry. The test on this while loop stops the iteration when the current node has passed beyond the end of the chain, in which case node before points to the last node and our add will occur after the last node. The second test is for when the value of the entry in the current node is greater than the value of the entry to insert. At this point, current node references the node that will come after the entry we're inserting, and node before references the node that comes before the node we're to insert. The body of the while loop moves the two references until they're correctly set. Let's see how this works for our example. The first iteration of the loop set node before and then increments current node. After the next increment of our references, the entry in the node referenced by current node is greater than the entry to insert, so our loop terminates. When the method ends, our add method has a reference to the node with the entry in sorted order that comes before the entry we're inserting. We then check to see if the node before is null or if the list is empty. In both cases, we insert our node at the head of the chain. Otherwise, we set node after to the next node in the chain and add our node as we did in the linked list add. Let's look at a recursive implementation of our add method. Our add method implements the interface of the sorted list.
So we had an iterative implementation. Now we're talking about a recursive implementation.
Interface, but our recursive method needs a different signature to function properly since we need a way to pass smaller examples of the problem in our recursion. Let's see how our recursive implementation would add oranges to our sorted list. As we discussed in our lectures on sorting, if a method, especially a recursive method, could change which node is the first node in the linked chain, it must return a reference to the new first node, even if it's not changed. The first call to a recursive method sets current node to reference the head of the linked list. Since this is not null and the value of this entry is not greater than oranges, we make a recursive call passing the next node in the chain as the first node of the smaller chain to search. Kiwis is not greater than oranges and it's not null, so we make another recursive call. For this call, current node references the node storing the entry peaches, which comes after oranges, so we execute our base case and create a new node that holds the entry to insert. The next field for this node is set to the node referenced by current node, and then current node is set to reference the node just created that is to be inserted into the chain. And we return current node to the recursive call before us and place that reference in node after, which is then used to set next on the node referenced by current node in this call. This call returns its current node, which references the node with the entry kiwis, and that is placed in node after. Here, since the order of the nodes does not change, node after already references the same node as the next field of the node current node references. So we, in effect, reset the next field to the same value. Returning from the original call, we use the value in current node to set the head to the correct first node in the chain. And finally, we increment number of entries to reflect that an entry has been added to the sorted list.
Okay, so it's kind of like we're able to go single step mode and have the authors tell us how it's working. And so that's what we saw with that example. Well, we'll just finish up with the sorted implementation of this. And depending on the time, I'll spend a few minutes to go over sorted list. I'll pull up Eclipse and you can see that, but it's just going to be reflecting pretty close to what we saw here in the video notes in the lecture as well.
As we noticed in an earlier lecture, the linked implementation of the ADT sorted list repeats much of the corresponding implementation of the ADT list. Can we avoid this duplication of effort and reuse portions of the list implementation? The answer to this question is yes. You can certainly use the ADT list to create and maintain an alphabetical list of strings, and it is natural then to consider using the ADT list when implementing the ADT sorted list. Basically, you can do this in one of two ways. Here, we'll use a list as a data field within the class that implements the sorted list. This concept is called composition and illustrates the hazard relationship between two classes. Future lectures consider a second approach using inheritance to derive the sorted list from the list. Our constructor uses the class LList, which is the linked implementation discussed in an earlier lecture, and that's an implementation of the interface list interface for the ADT list. Later, we'll look at the impact of selecting a list or our array-based list implementation as the data field. Implementing get position is the only difficult method to implement, so let's look at it first. This method must determine where in the list an entry currently is or where it belongs if it's not in the list. So we need to compare an entry to the entries already in the list, beginning with the first one. If an entry is in the list, we obviously compare entries until we find a match. However, if an entry is not in the list, we want to stop the search at the point where it belongs in the sorted list. We take advantage of the sorted order of the objects by using logic similar to that described in an earlier lecture. For example, suppose that the sorted list contains the 4 items: apples, bread, oranges, and pears. If we want to see where nachos belongs in the sorted list, we discover that as strings, nachos is greater than apple, nachos is greater than bread, nachos is less than oranges, and thus nachos belongs after bread but before oranges, that is, at position 3 in the sorted list. To compare an entry to an entry in the sorted list, we first use the list operation getEntry to retrieve the entry at a given position within the sorted list. Then the highlighted expression here makes the comparison. Similar to our earlier sorted list implementations, after the while loop terminates, we need to determine if the while loop terminated because we reached the end of the list or we found the entry. If we did not find the entry, we make position negative as a signal to our caller that the entry was not in the list. The method implementations of the ADT sorted list are brief, as the list will do most of the work. To add a new entry to the sorted list, we first use the method getPosition, which is an operation of the sorted list. Recall that getPosition finds the position of an existing entry within a sorted list, or the position at which we should insert a new entry that does not occur in the sorted list. GetPosition sets the sign of the integer it returns to indicate whether the entry exists in the list already or whether it doesn't. When adding an entry to a sorted list that can contain duplicate entries, it doesn't matter whether the entry exists in the sorted list already. Thus, we can ignore the sign of the integer that getPosition returns. Notice that our implementation uses the method absolute value of the class math to discard this sign. It also uses the add operation of the ADT list. We also use getPosition when removing an object from a sorted list. This time, however, we need to know whether the given entry exists in the sorted list. If it doesn't exist, we can't remove it. In such cases, our sorted list remove method will return false. Otherwise, we'll call the ADT list method remove to remove the item from the list.
I know there's a lot of information that we're covering here, and you can get a chance to be reviewing these videos again or stop them as you would like. But there's little snippets, little tips that they have been talking about. You might remember at the beginning, at the very last slide that I showed in the lecture, the comparison between the performance of a linked and an array implementation. And so this is that chart that we were getting a chance to see. And so for an array list, either using a sorted list or a list, it's exactly the same. So it's only when we have a linked list where we want to be avoiding using this list. And so they were talking about using the list when we're in array implementation and there's no hit for doing that. So that's one of the things I'll just point out as we're going through this.
Sorted list implementation uses a linked implementation of the ADT list to store the sorted list data. What would we need to change if we wanted to use an array-based implementation of the ADT list for our data? Well, since our sorted list implementation uses only ADT list methods, it's not dependent on how the list is implemented. So no methods in our sorted list need to be changed. The only change to our class is in our constructor. To use an array-based implementation for storing our data, we must instantiate an A-list object as our list. This then leads to the question, which implementation is better? Often the answer to that question depends on how you'll use the sorted list and which list implementation we choose to hold the data.
So I was just showing you this table, and you can see there's a situation with an array implementation actually performs a little bit better. But it also will depend on what you're going to be doing in your application. Are you going to be querying the get an entry very often? If not, then these could be pretty much the same.
This first table reviews the worst case efficiency of the methods in the 2 implementations of the ADT list. Generally, they're comparable, except for the getEntry method. The array implementation can directly access an entry, but the linked implementation must traverse the chain to that position, and so is of order at most n. That poor efficiency of the linked entry method is magnified since it's integral to the implementation of the get position method, add method, and remove methods in our sorted list. We have order of at most n squared in the while loop in our linked implementation of the get position method. The while loop itself must iterate through the list either to the entry or the end of the list. This is an order of at most n. Each of these iterations requires another pass through the list by the linked get entry method to find the entry at the requested position, which we saw was order of at most n itself. These two together give us order of at most n squared for the get position method.
Okay, sorry, those are a little bit longer than I would have liked to be devoting our time for video notes, but I do find it is another good way for us to get a sense to see what's going on. So I'll just end our time today looking at one example of a sorted list, and this is going to be the array version. And so this is the one that we just saw here. So you saw the sorted list interface. And so as we did in the lecture notes, it just showed you the more details here. There was a scenario where they had 2 removes. We only have 1, so we see that. And then we have all of the other methods that remain the same for when we go from a list to an array list. So then we have the array implementation. We have a lot of the things that we're familiar by now in terms of the constructors, the default constructor. If we don't say what the size is, it uses the default capacity, and then it has everything set up like that. So we do the add, and so we get the absolute value of what is the value at a given position. And so this is we get the absolute value of the position. So we get the new entry position. Remember, there was a scenario when we made it negative if we were trying to specify that if it's in the list or not in the list. We have the current index. We set it at the beginning to the number of entries. And while the current index is greater than or equal to the new entry position, then what we do is we make space for where we're going to be putting in the new entry. And so then the new entry goes in that position where we've created, and we increment the number of items. For the remove, it's going to be, in a sense, kind of the reverse of that. And so we set the Boolean found to false. And then as long as what we have for the array is not empty, then we can keep going through this as we set the position to the get position of an entry that's passed to this method. We have an assert statement. We really haven't talked about too much, but this is just another way of just double checking if this assertion doesn't come true, then it's going to let us know. And so we're asserting that the position is not equal to 0. So if the position is greater than 0, then we have to be removing the gap. We decrement the number of entries, and we change the Boolean for the found to true. And then we return what it was found, the Boolean value there. The get position is the other one that is new. And so we initialize the position to number 1. And so we could put this in. The assertion is that the number of entries is greater than or equal to 0. And so get entry calls check integrity. So we do not have to. So this is like some of the things that we've seen in some of our other code for when we do an array implementation. We have this kind of capability where we look at the check integrity to make sure that everything looks fine. And then while the position is less than or equal to the number of entries, and an array and the n entry when compared to the position is greater than 0, then we're going to do this. We increment the position. And then so thus we find out where we get to the right position. And then if the position is greater than the number of entries, or we do the not version, so the opposite of an entry is equal to get entry at position, then we do the negation of that. So this is how we're trying to indicate that there isn't something there. It's not in the list, and then we return the position. So those are the 3 methods that we talked about that are new. Everything else is the same, so we don't need to go through those in detail. Then we have a driver. And so remember, a driver is like, so someone in the backend implementation, they're just trying to verify what they're exposing to the end user is working. And so we have that laid out here. And so since we're just about out of time, I think I'll just go run this so we can just get a chance to be seeing what's laid out here. And so we didn't get any error messages. And what they do with here in the code, and since this top one is a little bit bigger, I'll just go with that. So we create a new sorted list with no entries. I think we're running over, so I think I'll just quit it there. So I think those are the main points that I was hoping to get a chance to convey today. So sorry for going a little bit long. Any comments or questions on what we shared today? Or if give me a thumbs up if we're tracking what we've got. Okay, well, please do reach out if you would like to go over this a little bit more. Also, the lecture is recorded, so you can take advantage of that as well. All right, well, the Lord bless you guys. Have a wonderful day. I look forward to seeing you next Tuesday.
Thank you.
Take care.